So, the homework. You guys are going to participate, so I'm going to be calling on people. So make sure you're following along so that when I call on you, you don't go, because nobody likes that. Okay, so numbers 1, 2, and 3 were all similar. I'm guessing everybody probably put the same answer for all three of those. I want to make sure you have the right same answer for all three of those. So, I don't know, Nate. Number 1 says, what is needed to cause a box to move from rest? What did you write? Ooh, very good. A lot of people put force, I'm guessing. Yes?
Yes.
All right, force is a very good answer, but there is a slightly better one. Okay? Sure, what do you got, John?
Net force.
Awesome. Yes, net force is a better answer. Let's make sure everybody understands why. Force isn't wrong, per se. Okay? But there's a better answer. All right? So here's why I like the answer net force better. All right? So, thanks, John. So the question says, what is needed to get an object to move from rest, right? So I've got this chair here, right? Right now it's at rest. So if you tell me that force will get it moving, then that makes it seem like force will get it moving. But here I've put a force on it, but I have not gotten it moving, right? So the problem here is that my force isn't the only one on it, right? What other forces act on the chair besides me, you guys? Okay, gravity and the floor holding it up, those cancel out, so we don't need to worry about those. And friction, right? So the idea is if I'm pushing this way with 5 newtons and it doesn't move, friction must be pushing back with, well, not greater than 5, with exactly 5, right? Because if it was greater than 5, then it would be moving towards me, right? Okay? So I'm going to try 10 newtons. It still doesn't work. So friction must be pushing back now with 10 newtons, right? But 11 newtons, now it moved. So what must have just happened there to get the chair to move? Why was 11 newtons successful? Thoughts? Sure, what do you got, Tim?
Because that was enough newtons to sort of override the friction.
To override friction, right? So it seems like maybe the most force friction could exert there was 10 newtons. So my 11 produced a net force of 1 newton, right? Okay? So remember, you guys, the whole premise behind this section is, oops, why are you being stupid? Clearly, that's not my smart thing. Oh, I see. It's because my board needs to be calibrated. Aha. I'm going to do that right now. And you're going to have to wait. Doot, 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 doot. I'm going to stop saying doot now. Somebody else is going to do it for me? Okay, so the whole premise behind this sheet, you guys, is this, that if your net force is 0, then your acceleration is 0, and your velocity is constant. All right? So, if you're trying to get something moving from rest, do you want the velocity to be constant? No. And that means that our net force can't be 0. Follow? All right. Any questions with that? Nate, do you see what I was getting at there?
Yeah.
Are you lying so I'll leave you alone?
No.
Okay. Does everybody see what I was getting at there?
Yes.
LaShawn, you good? Mm-hmm. Yeah? Okay, I just saw a little, you're good?
Oh, yeah.
Okay. All right. So one quick thing that has come up in my other hours that I want to make sure you guys are aware of. So when we say that the object has a net force on it, we're implying that the net force is not 0. Okay? And saying no net force is the same as saying the net force is 0. Follow? Yeah. All right, cool. All right, so any questions with number 1? All right, so then 2 is the same idea. If you want something to stop moving, then a force is good, but a net force is better. Okay? And in fact, anytime you want to change the velocity, that means you want your velocity to be not constant. And so for number 3, anytime you want to change the velocity, you want your net force to be not 0. Good? Any questions on 1, 2, or 3? Everybody happy? I'm going to put these pens down now. Alrighty. Numbers 4, 5, and 6. Well, 4 and 5. Number 4, if there are no forces on an object, does that mean that it is not moving? Elena, what'd you put for that?
No, because it could already be in motion.
Good. It could already be in motion. So that would mean that if it's moving now, it would have to be moving with constant velocity, right? Can somebody give me an example of something that sort of satisfies that? Sure. What do you got?
Throw a
Alex, sorry, say it again.
Just like throw a puck or hit a puck on frictionless ice.
Okay, good. Yeah, a hockey puck, after you've hit it, or kicked it, or thrown it, or whatever, is just going to keep sliding, right? Because there's very little friction there, right? Cool? All right, cool. Number 5, if an object... Oh, yeah, what do you got, John?
Oh, no, I was just gonna...
Oh, okay, sure, what do you got? It says if an object is not moving, does that mean there's no forces on it, and why?
There could be a force, it's just not strong enough to move it.
Okay, so why would a force not be strong enough to move it?
I don't know, it was weak. It wasn't as strong as a net force.
So, what's wrong with that? That sounds funny to me. I don't know that let me come back to you in 1 second, okay? Abby, what were you going to say?
I was going to say that I said that the forces acting upon it could be enough to cancel out. So it
Okay,
might be enough.
so if all of the forces cancel out, then you just said it while I was talking?
There would be no net force.
There'd be no net force. Good. All right. So the reason why your force might not be big enough to move it is because there might be some other force canceling it out, making your net force 0. Does that make sense? Everybody? Yeah, Alex?
You say like an equal and opposite force.
On the object, yeah, that'd be fine. Yeah. All right. Good, you guys? All right. And so, I mean, that's this, right? Look, there's a force, but it's not moving, right? Because my force wasn't big enough to overcome friction, so the net force is still 0. Cool. All righty. Any problems up through number 5? All right. I don't know. Noah, what'd you put for number 6? It says, can an object go around a corner with no forces on it?
I said no.
Okay. How come?
Because in the notes you said that you need a force to go on first.
Okay. So relate it to this garbage up here. I don't know. I'm saying garbage, but what does it have to do with all this? If you go around a corner.
Well, I guess you would need force to like turn.
Okay. Why is turning important? It has something to do with one of these 3 things up here. Give him a second, you guys. Let him think. You remember? Or no, sorry, totally on the spot here. Okay. So turning is important because it implies direction, right?
Oh, yeah.
So why is direction important?
Because these are all vectors.
Okay, these are all vectors, and in specific, one of them deals with, well, sure, what do you got, Brian?
Acceleration is the direction.
Okay, yes, so if you're if you're changing direction, you're accelerating, but I want a little bit of a better reason why. Sure, why am I forgetting everybody's names today? What is wrong with me? I'm going to come back to your name, but answer the question.
When you turn, your velocity changes.
There you go. Your velocity changes, right? Okay. Velocity is speed and direction. Okay. And so when you turn, you're changing your velocity. There must be a net force. I want to say Dylan, and that's totally wrong. I'm going to get it before the hour's out without looking at anything. I don't know why I'm drawing a blank on this. Okay. 5 letters. It's consonant, vowel, right?
I don't know.
Yeah.
See, this is weird, right? My brain is messed up. All right, I'm going to get it. Hold on. I know, isn't that weird? I don't know. I just can't remember what the vowels and consonants are. All right. Okay, so is everybody good up through number 6? Okay. All right, number 7. I feel like we haven't heard from Ben today, right, have we? Ben is over here. Oh, man. What just happened?
I don't know. I don't see you wrong.
Hi, Ben. How are you? Nice to meet you. My name's Mr. Hecker. Your name is Ben. Number 7. A hockey puck is sliding across frictionless ice at 6 meters a second. What'd you put for the net force?
It's 0.
Good. It is 0. Can you tell me why it's got to be 0?
Because there's no net force action on it.
Good. Yeah, there's no forces on it, right? You don't need to have a force on an object to keep it moving, right? Cool? Everybody good?
Yeah.
All right. Number 8. So here's where things start getting a little bit weird. It says you push a large box across the floor at a constant velocity of 6 meters a second, and it wants to know the net force. All right, so check it out. So here's the floor, here's the box. We are told that it's moving at a velocity of 6 meters a second. I'm going to make a little note that it's constant, right? Lucas. All right, so the velocity is constant. Sorry about that. I don't know where that came from. So the velocity is constant. Now, are there any forces on the box according to the problem? Let's see. The first two words in the problem are you push. Oh, a push is a force. That means you're pushing it, right? So there's got to be the always amusing force of U, Fu. It's going to happen. So just get it out there. It's force of U. All right? Cool? Now, the fact, though, that this velocity is constant automatically tells me something super duper importante. Net force has got to be 0. But wait a minute. If you're pushing it with some force, then how could the net force possibly be 0? Tom Wilkinson, what are you thinking?
An equal force is opposing.
There's got to be something pushing this way. And it doesn't tell you what it is, but you could probably make a pretty safe guess. Friction. Good? All right. Now, so that means that since it's moving that way, the force of U must be bigger, right? No. They have to be the same. Why? Because the net force has got to be 0. So if you're pushing with a force of arbitrarily 200 newtons, then that means the force of friction has got to be negative 200 newtons. And this is where a lot of people are like, no way, Mr. Hector, you're lying to us. How can this thing be moving? These two forces cancel out. There can't be any motion. Right? It's like a tug of war with both teams even. They cancel out and the rope doesn't move, right? But no. This could be moving at a constant velocity. Okay? So, for a minute, I'm going to jump ahead to number 12, because I think number 12 does a really good job of putting a fine point on how this is possible. How we can have an object where the forces cancel, but it's still moving. Okay? And then I want to show you a demo that illustrates problem number 12 that will help you better understand. Good?
Yeah.
General questions before I go on. Okay. So, Jack, you're on deck, now that I remembered your name. How are you? Good. All right. So number 12. Oh, I don't know why I can't remember names today. I don't know what's wrong with me. Okay. Number 12. A says, suppose a box is sliding on a frictionless surface at 5 meters a second. A says, what will the box do if no other forces act on it? So first, let's draw it. So 12A. Here we go. We're doing it in red. So here is our box. It is sliding along at a velocity of 5 meters a second. And there are no other forces on it. So, Jack, what's going to happen?
Just going to continue moving
Good. How come?
because there's no other forces acting on it.
Yeah, there's no forces on it. So that means my net force is 0. That means my velocity is going to be constant. Can you give me a number? At 5 meters a second, right? Because there's no net force, right? Is everybody good with that?
Yeah.
All right. Now, in part B, it says, what would happen if the box is sliding along at 5 meters a second, and Roy comes along, he gets behind it, and he pushes it forward with a force of 10 newtons. So here's the force of Roy, 10 newtons. Okay, is it 5? Is that right? Do I have the numbers right here? Or is it supposed to be 6? It is 5. Okay, cool. So, Joey, I know you were out yesterday, but just what's your intuition to this? What do you think this box is going to do?
The box is going to go to the right.
Okay, it's already doing that,
Yes.
right? It's already moving to the right, and now we've pushed it to the right. So tell me what's going to happen while it moves to the right. Is the velocity going to stay constant? Do you think it's going to keep going 5 meters a second?
What number is this?
12B. Sorry, once again, totally on the hook.
No, because
Here, let's try it. So we need an object that's moving this way, right? What's it going to do if I push it? What'd you do, you guys? Sped up, right? It's already moving that way, so if I push it that way, it's going to keep going that way, but do it faster, right? Does that make sense, Joey?
Yeah.
yeah,
I don't believe you.
it makes sense.
Okay. All right, so it's going to speed up. I'll show you a demo that'll help hopefully solidify this. So the idea is Roy's force makes it speed up. I'm going to put it speeds up. I don't know why I feel like that's better. All right, are we good? Okay, cool. The idea here is the force is in the direction of motion, so it's going to go faster in that direction. It's going to accelerate in that direction. Okay, Alex?
We can't determine how much faster because of different units, correct?
Correct. That's Newton's second law, which you're going to watch over the weekend. So we'll get there. All right, so is everybody good?
So,
Yeah.
so because it accelerates, the velocity isn't constant.
Correct. That's exactly correct. Because the net force isn't zero, right?
Right.
So the velocity can't be constant. Everybody follow? All right. So part C says, what would happen if, instead of Roy pushing it forward, what would happen if it's sliding along at 5 meters a second and Sally pushes it backwards with a force of 10 newtons? So, what would you say, Milena? Okay, you're close. But, so, you remember in the video Superman trying to save the baby from getting squished by the bus? Right? So, which point for me? The school bus was moving this way, right? Okay, and what did Superman try to do to it? Stop it by pushing it this way. Did the bus immediately start moving that way? No, it takes a minute, right? Because before it can move that way, it's got to stop moving this way. So in this example, the box is moving to the right at 5 meters a second. And then Sally pushes it backwards. This is Superman stopping the sliding bus. So eventually, if she pushes for long enough, it'll go that way. But before that happens, the box has to stop. And before it's got to stop, it's got to slow down. Right? Look, her force is working against the velocity. It's moving this way, we're pushing it that way. And as a result, it slows down. Cool? Does that make sense? All right, let me show you these before we get to D, since it seems like some of you guys are, this is not super intuitive for some of you, which is fine. That's why we're here, right? Okay, so check it out. So here's my two cards. Pretend they're glued together. I didn't tie them together because it doesn't really matter for what we're doing here. But all right, so if I push the two carts this way at 5 meters a second, then they just move at a constant velocity of 5 meters a second. Why are you guys not staying together all of a sudden? What's wrong? Come on, snuggle up. There we go. Fine, I'll just take you together. You guys will be friends and you like it, damn it. To the basement. Eat your mashed potatoes. All right, sorry. Okay, so there we go. They're moving at a constant velocity, right? Everybody good? Yeah. All right, so that was example A. No forces. Oh, look, they move at a constant velocity, right? Okay, B. We need Roy to push them forward, right? So here's the deal, you guys. Part of what makes forces difficult is that in a daily life, when you push stuff, you sort of don't have a way of sort of registering how hard you're pushing, right? Like when you walk, you guys all know what 4 miles an hour looks like, right? Right? Or 10 miles an hour or whatever. So you sort of have a sense for like, oh, I'm walking really fast right now because I'm jogging or whatever, right? But when you push something, like I have no idea how much force I just exerted. All I know is I pushed it. Do you know what I mean? And so that makes forces tough to study. All right, so what I've done here is I've replaced me pushing with these fans. And the idea is the fans exert a fixed amount of force. Okay? So, yeah, right?
How do you know when the velocity outweighs the force? So like when would it actually start going?
Well, that's sort of so I'll say two things. That's basically what the second law tells us. You're going to learn that in the next video. Okay? And the question, in a sense, doesn't make sense. The force can't outweigh the velocity because they're different things.
So like if velocity's going that way and the force is going that way, when will it start going?
Okay, gotcha. That's the second law. So we'll get there. Okay? And I want to make sure you guys understand, you can't compare force and velocity. Like, it doesn't make sense to say, oh, the force is more than the velocity. All right? In the same way, and I think I said this to somebody yesterday, it doesn't make sense for me to say my weight is more than my age. Right? Like that doesn't, 150 pounds is more than 43 years. Like, that doesn't make any sense at all, right? Okay? So similarly, it doesn't make sense to say that force is more than velocity, or vice versa. Follow? All right. And the spirit of your question will be answered in the next video. Okay, it's Newton's second law. All right. So, let's do this again, but let's have Roy push it forward. All right? So what I'm going to do is I'm going to switch on this fan here. And so what the fan is doing is it's pushing the carts this way. All right, so what happens while the fan's pushing? It goes this way at a constant velocity? No, it speeds up, right? Watch it again. See it? All right, so that is example B, right? Roy pushes it forward, it speeds up, right? All right, so now let's do example C. I'm going to have it move this way, but I'm going to have Sally push, which is this way. Okay, so right now we're pushing that way, right? But we need an initial velocity that way. So, initial velocity that way, Sally's pushing back. It slows down, doesn't it? And eventually it comes back, but not immediately, right? So the fan is Superman trying to stop the school bus. So here's the school bus sliding. Is it going to stop it in time? Hooray! And then if he keeps pushing, then it goes back the other way. Okay? So this right here is example C. It's moving to the right. Sally's pushing back. It slows down. Eventually it'll stop and then go the other way. Alex, what do you got? Sorry?
Never mind.
You sure?
Yep.
Milena?
So if we didn't put slow down, would I be wrong?
Yes.
Okay.
Yeah. What did you put?
I went and moved left.
Okay, so that's true eventually, but might not necessarily be true. Okay, here's a simple example of when it wouldn't be true. All right, I'm going to push this whole chair that way. I'm just going to give it a shove. Okay, after I let go of it, point for me. Which direction is it moving? That way, right? What's the only force on it? Friction. After I let go of it, the only force on it is going to be friction. Point for me. Which way does friction go? That way, right? So isn't that the same thing as example C? Oh, shit. Oh, that censored if you're watching this video at home. Because I'm recording this. You misheard me. I didn't say that. It was shit. All right, so anyway. So did it come back ever? No, because friction's not going to make it come back. Good? Okay. Are we good? All right. I apologize for my horrible language. All right, so is everybody good through A, B, and C? I'll get them later. Don't worry about it. All right, because I want you guys to hear part D, which is the most important part of this. So part D says this. What would happen if the box is sliding along at 5 meters a second and both Roy and Sally push it? So, Roy is pushing with 10 newtons. Sally pushes back with negative 10 newtons. Abby, question or answer? Answer. Okay, hold tight for 1 second. So let's try to, without even thinking about it, let's just process the rules that I told you. Right? So Newton's first law says if the net force is 0, then acceleration 0 and velocity is constant. So in this example, the net force is 0. That says net force. Oh, well that means then that the acceleration is 0 and therefore my velocity is constant, right? At 5 meters a second, right? So that's the answer, but that doesn't sort of lend any intuition as to why it's true. All right, so let's take a step back. In our first example, Roy pushed it and he made it speed up. In the second example, Sally pushed it and she made it slow down. All right, what I want you guys to remember is force doesn't, you don't have to have force to have motion, you have to have force to have a change in motion. So in this problem, in simple words, what's Roy trying to make the box do?
Speed up.
Speed up, right? In simple words, what's Sally trying to make the box do? Slow down. Who's winning that battle of speed up versus slow down? Nobody. So it doesn't speed up, it doesn't slow down, it just goes at a constant velocity. Because Roy's attempt to make it go faster are canceled out by Sally, and Sally's attempt to make it go slower are canceled out by Roy.
I have a question. Could you repeat what you said about, I think you said something about force that needed to change motion?
Yeah, I said you don't have to have a force to have motion. You have to have a force to have a change in motion. I guess technically I should say net force, but good? All right, so the answer to D is exactly the same as the answer to A, isn't it?
Yeah.
Because they both have the same net force, the same constant velocity, right? So what I'm saying to you is that A is this. Turning on both fans will give us the exact same result. Right? Those two forces are canceling each other out, but we still get motion Because the forces of the two fans are exactly canceling each other out. Make sense?
Sorry, one more thing.
No, don't be sorry. You're good. What do you got?
You said that a net force isn't needed to cause motion, but can a net force cause motion?
I hope I didn't say that. You need force. You can
force
have motion without a net force.
Pardon?
Here's why I'm hesitating a little bit.
Okay.
So if something isn't moving and you want to cause it to move, you absolutely have to have a net force.
Gotcha. That's what that was my question.
Okay. Yeah. So I'm sorry if I said otherwise.
No.
Okay. All right. Does this make sense, you guys? I know this was elaborate, but I want to make sure you guys understand because so often I see people look at this and they go, oh, forces cancel out, it's not moving. And that's not right. Forces cancel out, it's not changing how it's moving, is what you should say. Follow? Any questions? Okay, cool. So I think that hits the bulk of the tough stuff here. Let me plow through the rest of this and then show you guys a couple of the demos. And then I guess that'll be it. Okay, so so that was number 8. So are we all good with 8 and 12 now?
Yeah.
All right, 9 is exactly the same as 8, except it's going faster, right? So whether I push the carts slowly or I push the carts quickly, they still have a net force of 0, right? So 8 and 12 are exactly the same thing. Number 10 is a little silly. If you're sitting at rest in a chair, I guess technically there are 2 forces on you, right? Gravity and the chair. Okay, but if you ignore those, then there's no forces on you, which is why your velocity is constant at 0. Number 12. Any car driving down the road at a constant velocity automatically has a net force of 0, right? Because the velocity is constant. What forces are there? We'll learn more about this when we get to the third law. So for now, if you wrote the force of the engine pushing the car, or the force of the tires pushing the car, or the gas pushing the car, or something like that, that's fine. And then that force is canceled out by friction and air resistance. Okay. All right, we just did 12. All right, 13 and 14 I think are the last 2 that I want to talk about. So any questions on 1 through 12 before I do 13 and 14? Okay, so 13, a minute ago I dumped all these scales on the ground. How'd that happen?
You push the chair.
Okay, so that was a force of me pushing the chair.
They were going
Why did the box slide off? What? So what happened? Friction stopped the chair, but the box kept moving because plastic on plastic is slippery. So there's not no friction, but very little friction. There wasn't enough force to stop the box, and the box kept sliding, right? Okay? Number 13, the car driving into the brick wall, is the exact same thing. Okay? On a test, this problem would be 4 points. Okay? Here's the deal. Roy's not wearing a seatbelt. He drives his car into a brick wall. He's screwed, right? So why? Well, let's think about it. So before the collision, both Roy and his car are moving along 60 miles an hour, right? An object in motion stays in motion. As long as there's nobody in the way, still 60 miles an hour. You got to keep making the sound effects or it won't work. Okay? Then what happens? What hits the brick wall?
The car.
The car. So remember yesterday I said every force has 2 objects associated with it? The object being pushed or pulled and the object doing the pushing or pulling? So what's happening there with the wall and the car?
The wall is pushing the car.
The wall is pushing the car. That's why the car stops. If the wall didn't push the car, it would have kept going, right? So the car is driving along at 60 miles an hour. Its velocity suddenly changes to 0 because the wall puts a force on it. Good? So that's why the velocity of the car changes. Now, what about Roy inside the car? He keeps going at 60 miles an hour because there's no force on him because he's not wearing a seatbelt. Make sense? Anybody skateboard? Anybody ever hit a rock on a skateboard? Like the worst thing that can happen to you. Right? Because what happens? You go flying forward, right? Sort of, but you were already going forward, right? So really what's happening is the skateboard stops and you don't. Make sense? And it sucks. Okay? Questions? All right. 4 points. 2 points to tell me what happens to the car and why. 2 points to tell me what happens to Roy and why. Use the word force and velocity. the velocity of the car decreases because of the force of the wall. There's no force on Roy, so his velocity stays constant. Cool? Questiones? I will let everybody write that down while I have a sip of my water, because I am thirsty. I believe that water is several days old. Gross. All right, number 14. All right, so number 14 it's number 13 played in reverse. So let me see if I can make this work. I'm going to try to use a bigger object for the body. This may not work. We'll see. All right. So usually when you get rear-ended, you're sitting at a red light or a stop sign or something. You're already not moving, right?
Yeah.
And then some guy behind you is eating a submarine sandwich. He's not watching what he's doing, and he drives into you, right? So here's your body. Here's your head. My hand is going to be, oh, no. Nuts. Sorry. This is what I was worried about. All right. So body, head, my hand is the seat. Cool? All right. So I'm facing this way. I'm waiting for the light to turn green. Okay. The guy behind me isn't watching what he's doing, and he rear ends me, right? So that interaction is a force between the two cars. His car pushes my car forward, right? But my seat is attached to the car, and so when he pushes the car forward, he's also pushing my seat forward, right? Okay? Well, guess what? When the seat moves forward, it pushes my body forward, right? But not my head. So watch what happens. You get rear-ended and bam. Okay? All right? And your head falls off, right? No. All right, so in real life, obviously, your head doesn't fall off. But what I want you to realize, a lot of times when people visualize you getting rear-ended, people visualize your head snapping back. And that's not really what happens. When you get rear-ended, your head doesn't snap back, your body snaps forward, and your head gets left behind. Okay? Now, in real life, your head doesn't fall off because your head is attached to your body by your neck. So what provides the force that drags your head along? Well, if there's a headrest, yes. But if there's no headrest, your neck exerts that force, right? And that's where the whiplash comes from. Your neck exerts a tremendous amount of force to pull your head along with your body. Okay? So what does the headrest do, you guys? It does not keep your head at rest. Your head's already at rest. It pushes your head forward with the rest of your body. Look, the seat's pushing your body forward, right? The problem is nothing pushes your head forward. So if we put a headrest there, that headrest will move your head along with your body, keeps your head in line with your body, and prevents the whiplash. Does that make sense?
So the headrest provides,
See if you can finish it. What do you got? The headrest provides what?
a way for so that your head is able to follow the rest of your body.
Yes, so let's replace, you said it provides a way. What's it doing to your head?
It's putting a force.
It's putting a force on it, right? So it moves your head along with the rest of your body. Does that make sense, you guys?
Yes, sir.
All right, so instead of what we had before, you have, right? And see how my fingers move the ball along instead of the ball getting left behind? Okay, it's the exact same thing as the dishes, right? Yesterday, the tablecloth being ripped out from under the dishes is the same as when you get rear-ended, your body being ripped out from under your head. Make sense? That's sort of a graphic, but follow? All right. Any questions on problems 1 through 14? All right, and then 15 through 20 are all super quick. 15, if you fire something in outer space, what's it do after it's released? Keeps going, right? Because there's no forces, right? So the velocity is constant, right? 16, the law of inertia. An object at rest stays at rest, object in motion stays in motion. So it applies to both objects in motion and objects at rest. 17, if you've got a stack of books on a cart, when you push the cart, that's a force that moves the cart. What moves the books? Something. Otherwise they would stay at rest, like your head when you get rear-ended.
friction.
Well, it can't be the same force you're exerting on it unless you push the books and the cart.
Is it the force of the water?
It's hard.
What do you think, Alex? You get your hand up, what are you saying?
Like, are the books above the cart, they just fall back? Are they like in the cart?
No, it's like a flat top cart. So here's the cart, and then here's the book sitting on top of it.
Oh, it's the back of the cart that.
And there is no back. Well, why can't you picture what's in my head? Come on. Sorry. Lucas, you got an idea?
The friction?
Yeah, so the friction between the cart. Like if you look at most of the carts in the school, they have a little rubber surface on top. Okay, that provides more friction so that when you push the cart, the things that are on the cart don't slide off of it. Okay? Apparently a drawing would help that, yeah? Okay, I can do
And
that.
it was like the head thing, like you pushed it.
Yeah, I understand now exactly why you were confused. So that's my B. I will fix it. All right, so anyway, the point though, you guys, is that you need to make sure that you understand in order for object A to push object B, they have to touch. Okay? And if you're not touching the books, you're not pushing the books. So something else has to be pushing them. Follow? All right, the only exception to that rule is gravity and like magnetism. Okay? Those are the only two forces that work without contact. Okay? And the electricity too, which we'll get to later. All right, everybody good?
I
Yeah.
don't understand, so you're pushing the cart forward, but then the force of friction is what's causing the books to slide
It's
off.
preventing the books from sliding backwards.
Oh, prevent, oh.
So to prevent the books from sliding backwards, you'd have to push forward, right? Remember, it's resisting the motion of the books. So. Everybody good? All right. And then 19 or 20 and 20 are done, so we're going to just not worry about them. All right. Any questions about anything we've discussed today? All right, so the last thing I want to show you guys, if there's time, which I think there might be, and if there's not, then we'll finish it up on Wednesday, is I want to show you guys. So yesterday, I showed you guys the motion of this cart. Okay, so yesterday we looked at the motion of this cart, right? And so this is basically just a redo of the demo we did yesterday. So right now the velocity is 0. Push. Well, that's not at all the right thing. Hang on, sorry. There we go. All right. You know what? I'm not going to have time to do this justice. Let me do this. I'm going to hold off on the demo here. Let me do this. Okay, so one of the other things that I wanted to do today, I'll do this other demo on Wednesday. You guys have no idea what a Newton is. So Newtons measure force. In the video I told you guys another unit you could measure force. Anybody remember? Pounds, right? Okay? Pounds is also a measure of force, right? What do you measure pounds with? What do you, like if you want to figure out how much you weigh, use a scale, right? So same thing. To measure force, we use what's called a spring scale, okay? So I want to pass this around. These are calibrated. One side has markings that are newtons. One side has markings that are kilograms. Do not look at the kilogram side. You'll go blind, okay? You should also look at the newton side, okay? Because kilograms doesn't measure force. It measures mass. We want newtons, okay? So what I want you to do, I'm going to pass these around. These red scales go up to 20 newtons. So I want you to use your pinky and pull and exert 1 newton of force. It's almost no force at all, okay? And then I want you to pull harder and see if you can get 20 newtons. Okay? So 20 newtons is exactly how much force I'm exerting right now. It's not that much force. All right? 1 newton is not a large force. All right? And I want you to be aware that you can exert that 20 newtons by pulling or by pushing. Cool? Alright, so I'm just going to pass these around. I'll give one to each row, play with it for a minute, get a sense for what 1 Newton of force feels like, and then your homework is to watch the video. Alright?
Is the other one, the other worksheets on Monday?
I know.
The other one.
I know exactly.
And Sunday, the second guy, that's